Very good morning to all of you. I welcome you for this 9th session. 8th session we talked about dynamic programming etc. So, let us review some of the concepts that we discussed in the last session. Last session I introduced you the notions of dynamic programming. We discussed about how to solve the traveling salesperson problem as well as the knapsack problem. So, you can recollect in the last class we talked about the traveling salesperson problem. I was telling you that you will be given a directed graph where you have vertices as well as the edges. The traveling salesperson problem is you have to start from the vertex 1 and you have to visit all other vertex only once, and then you have to get back to your original city. So, that is called a tour. If you start from a place and then traveling through all other vertices and reaching that same vertex is called a tour, and every edge is associated with a cost factor. So, if you add all the edge of the edge cost, you will get the cost of the tour. The problem is to find the minimum cost path that is present in the traveling salesperson problem. You can see this particular slide. So, we solved this problem in the last session. You can see there are 4 vertices that are available. On the right hand side, what is given is the edge cost of each and everything. So, we solved that problem using the recurrence relation. So, G of I comma S, where S is nothing but a set of intermediate nodes and that is nothing but your minimum. I was telling you that C of I comma j is the cost of the path from I to j plus G j comma, what it exactly means is that suppose if I make a transition from I to a intermediate node j, then what is the cost of reaching 1 from j. So, I can visit a vertex only once, therefore, S comma j is coming. That means, I am free to visit all other vertices that is present in S except j. So, you can see very well how this problem works. So, we are finding g of I comma phi, phi is 1. Therefore, we have seen from the previous matrix that g of 2 comma 5 is cost of 2 comma 1, cost of 3 comma 1, cost of 4 comma 1, all the values you can get from your earlier matrix. So, now we start with a condition that the number of intermediate node is equal to 1. Therefore, the problem becomes g of 2 via 3 I have to reach 1. So, that means this becomes the cost of 2 3 plus cost of starting from 3 and then reaching 1. So, 3 comma 5. So, that means this becomes the cost of 2 comma 3 is 9 and 3 comma 5 is 6. Therefore, 9 plus 6 is 15. So, in this particular manner I am considering all other possibilities like starting from 2 going via 4, starting from 3 going via 2, starting from 4 via 2 as well as 3. So, I am calculating all the cost involving one intermediate node. So, for the next iteration I am increasing the size to 2, that is the intermediate nodes to 2. So, now again as usual I will start calculating g. So, last class we discussed about all the things. Now, our possibilities is I am starting from 2, I am going via 3 or 4. So, that means it becomes cost of 2 3 and going via 4 and cost of 2 to 4 and cost of 4 via 3 to 1. So, this is dynamic programming. So, these things are already calculated in the previous step. So, all we have to do is we have to get the values from your previous steps and you can calculate 25, 25 and 23. Now, we can increase s equal to 3. This is what we want. I am starting from 1, I am going via 2, 3, 4 and then I am coming back to 1. This is the goal. So, again you can see very well by our logic it is minimum of 1 to 2 going via 3, 4, then cost of reaching 1 to 3 and going via 2, 4 and cost of reaching 1 to 4 and going via 2, 3. These are earlier values. So, by substituting that into this equation we can find that it is 35. Therefore, we can conclude that the optimal tour is of the cost 35. And how to find that? Please recollect, in the last class we were discussing, that is we have to note down the minimum that yielded and we have to note down that intermediate node so that we can trace the path also. So, you can see very well the minimum is 2 of 3, 4 is 4. So, therefore, you can see very well my optimal tour is starting from 1 and it has to go via 2. Then I have to see the next one, which is the optimal, whether it is 4 or 3. You can see the minimum occurs in 3. Therefore, my path is 1 to 2, then 2 to 4, 4 to 3 and then I am going back to 1. If we try to solve this problem in the conventional manner, this is the complexity. So, this is a space requirement which is not possible. This is an exponential category. So, that is why we are applying this dynamic programming. So, because of that the problem is solvable. Last class we discussed about the knapsack problem also. Quickly let me recollect what we were discussing in the last class. Last class we were attempting to solve this problem. We have 4 weights, we have 4 items. These are the weights, these are the profits. So, I was telling you that this problem becomes a dynamic programming and it becomes something like I can add the item if the addition of the item does not overshoot the capacity of the knapsack, otherwise I will not place that item. In that case the profit is going to be the earlier one. So, students, you can recollect last class we started. So, you can see very well I am adding the first item. So, it is going to be the maximum of 12 and 0. So, all you have to do is you have to substitute that into the equation. So, you can see very well gradually you can find the subsequent values. So, you can see we keep on calculating, we keep on populating that particular table, and when we end the process what we have is the cost, the maximum profit that you can get from this particular problem. So, you can see very well it is 37. Therefore, you can conclude that for this particular problem the maximum profit you can get is 37. So, how to trace it? Again, as usual, in dynamic programming you have to note down the minimum and you have to note down the way in which you reached that minimum and then you have to trace. So, 37 we have to compare that with your previous entry. Previous entry is 32, 32 to 32 and 37 is not equal. So, that means I am adding that item 4. So, I am putting that item 4 into the knapsack. So, the weight of the knapsack is now reduced by the weight of your item 4. So, you can see very well the weight is 5. So, the weight of 4 is getting reduced. So, that means it becomes 3. So, you are going to the third entry. So, 22 to 22 is same. So, that means you should not add this item 3 into the knapsack because they are equal. So, we are item 3 is not added, but you can see this 2. 22 is not equal to 12. Therefore, we are adding the item 2, and now your knapsack capacity is now reduced by the weight of the item 2. Then now it becomes 1. So, you go to the first item. So, this is not same as the previous one, therefore, you are adding your item 1 also. So, now you can see very well the maximum profit that you can get out of this particular thing is 37, and the item that you need to pack into the knapsack are item 1, item 2 as well as item 4. So, this concludes the knapsack problem, and you can see that dynamic programming involves the population of the table. The argument in favor of dynamic programming is that dynamic programming always gives a better result for the optimization problem. Since it involves a long-term decision, the quality of dynamic programming is always superior compared to your greedy approach. But one strong argument against dynamic programming that is commonly made is, why should I populate the entire table? For example, in one of the earlier session, I was discussing about permutation combination problem. Do you remember? We were talking about the binomial coefficient of 4, 2. You can see very well the problem starts with 0, 0. You may ask a question like this: if my requirement is 4, 2, why should I start from 0, 0? The reason is we have to populate the symbol table. Suppose if necessary, is it possible to avoid populating the entire table? Means it is possible, and that technique is called memoization technique. In memoization technique, what we will do is, you can see the slide, you will solve only problems that are necessary, and then you will solve it only once. So, memoization is another way to deal with overlapping subproblems in dynamic programming, and we implement this algorithm in an recursive manner. Suppose if we encounter a new subproblem, we compute and store the solution, and suppose if we encounter a subproblem that is already we have seen, so we will simply look up the answer and then we will simply reuse that. In other words, the logic of memoization is like this: if necessary, you calculate, otherwise you need not have to. So, I can convert all the dynamic programming into algorithms involving this memoization or memory function capability. So, you can see very well I am using the initialization step, and you can see the difference here. So, what I am trying to do is, I am trying to fill that with a initial value like this. It can be a infinity or whatever it is. Then what I will try to do is, I will try to find the logic, that is I am adding an item, suppose if the addition of the item causes a overshoot, that means I am not adding that item at all. In that case, the profit is not going to change. If that is the case, I need not have to recompute, but instead I will simply reuse that from the previous entry. And if the addition is not overshooting, then I have to take the maximum of the early profit as well as early plus the current profit, and then I have to add that into the table. So, in other words, you can see very well this is slightly different from your earlier version, that is you are calculating only if necessary, otherwise you are not going to touch up that particular thing. So, the algorithm remains essentially the same, but only difference is it tries to remove the memory constraint to some extent, in the sense that we need not have to bother about calculation of an entry if that entry is not going to change. So, the logic is very simple. Suppose if the earlier value is 12 and after computation it is going to remain as 12, means then why should I compute at all? In that case, I will simply reuse that earlier value. So, in that particular manner I can implement the dynamic programming. So, this is what concludes the discussion about dynamic programming. So, now we are going to the next unit. The next unit talks about backtracking, and unit 5 talks about branch and bound techniques, and these are called new design paradigms. Already we discussed lot of paradigms like divide and conquer, greedy approach, dynamic programming, etc. Something similar to that, we have certain additional paradigms called backtracking as well as branch and bound techniques. So, for these design paradigms, some knowledge of the graph theory as well as the traversal technique are necessary. So, this session I am going to introduce you some basic concepts of graph as well as DFS technique, and then we will try to see how this knowledge can be combined together to yield a new design paradigm called backtracking. And after that we will discuss how to use that design technique to solve various optimization problems that have been included as part of the syllabus. So, let me start with the discussion of a minimal graph theory. The elaborate version we will see in the next session. So, in this session I am going to start with a preliminary idea about graph as well as a traversal technique called DFS. You can see the slide. We have encountered this concept many times. A graph can be a directed graph or undirected graph. It can be a weighted one or unweighted one. It can be a cyclic or may not have any cyclic at all. In that case, it is called acyclic graph. So, you can see this is a graph where you can see these are called vertices and these are called the edges. Since these are associated with arrow mark, we call this as the directed graph or digraph. We have seen already that we can use adjacency matrix like we used in traveling salesperson problem, or we can use the adjacency linked concept where every node can point to the neighbors of that particular node. We can also store all the edges in the edge list. Once a graph is available, then we are searching for information that is present in the nodal values. So, the necessity is all the information is available in the root as well as the vertices of the graph. So, I have to read what is present there, but I can't use a ad hoc procedure. Reason is there is a possibility that some of the nodes might be missed. To avoid that, we require some sort of a discipline of visiting all the nodes, and that is what we call as traversal. So, many problems require processing of all graph vertices and edges in the systematic fashion. So, we are introducing the notions of traversal algorithms. There are many algorithms available for us. Out of all the algorithms, some of the important algorithms are depth first search as well as the breadth first search. This is what we are going to do as part of depth first search. We are traversing or visiting the node as far as you can. If you have not visited that node earlier, suppose if you encounter a node that has been already visited, then you backtrack and then you try another way. You can compare this with a maze kind of thing, where you are trying to go to the dead end, and if a dead end has been reached, you try to backtrack to the earlier node and then you try to visit all other nodes. So, you can see this particular graph. I am starting from here. So, now you can see very well with regard to these things, I have two neighbors. So, in the next stage, I am visiting to one neighbor. So, now the old neighborhood information is lost. So, now I am here, therefore, as far as I am concerned, the neighbor is this thing only. So, I visit this particular node. So, now you can see very well all the earlier information is now lost. So, now I am here, and as far as I am concerned, my next node is this one. So, now you can see very well this is a dead end. So, now from this particular node I can't proceed further. Therefore, what I am trying to do is I am trying to backtrack to the earlier node, then I am backtracking. Now, I am visiting this particular node which is not visited, then I am visiting the other nodes. Now, you can see very well all the vertices are visited, therefore, I exit from the algorithm. The advantage of this approach over the ad hoc approach is that in this approach you can see or you can ensure that none of the nodes are unvisited, that is the advantage. So, you can see very well I am going back to my earlier thing. So, this is the algorithm of depth first search. So, I am starting with U. I am marking U as a visited node, and for each vertex that are reachable from u, I am calling that as v, and if v is unvisited, I am going to invoke the DFS again with v. Initially, I assume that all the vertices are unvisited, and after making this assumption, I am going to execute my algorithm like this. This is one more demonstration I am wishing to give. Students, you can see clearly this is a graph. This is what I was telling you just now. This is called the adjacency list, where you can see very well I am noting down all the neighbors into a list. You take this particular node A, you can see the neighbors are F, B, C as well as G, and you can take B, I have only one neighbor, that is A. So, in this particular manner I can formulate the adjacency list. So, now let us try to apply this DFS for this particular undirected graph. Okay. Please remember this graph as well as the adjacency list. So, now what I am trying to do is I am trying to use the data structure called stack. You must have studied what stack is all about. It is called last in first out structure. So, the last entry is going to be the first entry that is going to come out. You know very well that stack has got two operations, one is pushing and another is popping. Pushing an item always go to the top of the stack, and popping of the item is means that the topmost item is coming out. So, what I am going to do is I am going to have a data structure called stack, and I am going to push all the neighbors into this particular stack. So, now there is a possibility that the node that has been already visited perhaps may come again and again, because this is a undirected graph. To avoid that, I am having certain conventions like this. Undiscovered means a node that is not encountered earlier. Marked means a node that is already visited. Active means the node that is under expansion, and finished means I have already visited and read the content of that particular thing. So, now you can see very well, you can see this simulation. So, what I am trying to do is I am trying to push all the neighbors of A onto the stack. So, now F, B, C, G are present in the stack. So, F is the newly discovered node. So, now I told you that in DFS all the earlier neighborhood information is lost, only the neighborhood of the current node, that is the active node, should be taken into account. So, F is taken. So, all the neighbors of F are pushed onto the stack now. So, now you can see very well the neighbors of F are A, E as well as D. Since we are going to read all the information that is present, the small exchange of these things does not matter, because we are going to read everything. So, I am entering the neighbor of this F onto the stack like this. So, now A, A is already visited, A is already visited. So, I am going to the next entry E. So, now you can see very well E is the newly discovered node. Now, I have to enter the neighbors of E onto the stack. So, now the neighbors of E are D, F as well as D. So, now you can see very well I am visiting E now. Now, G is the newly discovered node. Again, as usual, your DFS forgets your earlier information, it jumps to G. G as neighbor A and neighbor E. E is already red, so it is already marked. So, you do not mind that node now. You will go to A, this is also already a visited one, already marked. So, you have finished G because there are no more entries. So, you simply pop those things, you can see very well all things are over, therefore, you will pop it, then you will come to the next thing, that is E comma F. Now, F neighbors are E, E is already marked. So, it is of no use for us. So, you go to the next one, that is D. D is the newly discovered node. So, now you can see very well D has got two neighbors E as well as F. F already marked, it is of no use. Then E, E is also already marked, we have already visited and there are no more entries. So, therefore, in the next step we are going to popping of this particular record. E is finished now. Now, you go to your D, D is over. So, you go to your earlier record. So, D is already marked. So, now this record is also over. So, you are going to popping of this particular thing. Now, you come to A comma C. C is a newly discovered node. Neighbor of C is A. A is already marked. There are no more entries. So, this is finished. You will simply pop it off. You will go to the next one, A comma B. A comma B, B is a newly discovered node. So, the neighbor of B is A. A is already being visited. So, entry is over. So, it is finished, then you will pop it off. Then you will go to the last entry, that is A comma G. A comma G neighbor A which is already visited, therefore, this is also finished. So, that means you can see very well all the neighbors of the first part is over. You have one thing that is loosely available as H as well as I. So, you visit I is a newly discovered node. So, you can see very well the neighbor of I is H. So, H is already marked. So, finished I, you are going to popping off, H is also finished. So, you will finish with everything. So, now you can see very well you are reading that in this particular order only. This is what we call as a DFS for undirected graph. What will happen if the graph seems to be a directed graph? Again, let us try to simulate that. You can see very well this is your directed graph. Handling directed graph is slightly easier than your undirected graph, because in undirected graph there is a possibility that the node will come again and again. So, let me show you the simulation of directed DFS for this. Again I am starting from A, the neighbors are F as well as G. I am going to F now, neighbor of F is E, then I am going to E. From E I can visit C, D as well as G. So, from E I am visiting C, from C I can visit A and D. So, A is already visited. So, you are jumping to the next entry D. So, from D you can have neighbor as C as well as F. C is already visited. So, you are going to F. F is also visited. Therefore, there are no entry. So, it is finished. So, you are popping off. Now, you are coming to C to D. So, now you can see very well both A as well as D have been read out. So, there are no more entry. So, you can pop it off. You come to the next entry of the stack. So, next entry is D. So, I can go to the next entry E to G. So, G is a newly discovered, but G has got no neighbor. So, that means I am visiting that and there are no more neighbor, therefore, I am popping off. So, now all the entries of this entry have been read, therefore, I am popping off. So, now you can see very well F and E both are read. So, that means I am popping off that also. Now, G, there are no more entries. So, again I can pop it off. So, now you can see very well this is how we are going to read all the things, and you can see very well. So, in this particular logic this particular part is totally disconnected from all other thing, therefore, this particular part remains unvisited. So, students, we will have a small break, and after the break we will continue our discussion. Thank you very much. Good morning friends, welcome back after this break. So, we were discussing about graph traversal. I was telling you that traversal means visiting all the nodes. If we visit the nodes in an ad hoc manner, there is a possibility that some of the nodes might be left out. So, to avoid that, we are going that in a disciplined manner. One is called the depth first search and another is called BFS, that is the breadth first search. So, we were discussing about BFS. So, the logic we have seen, we have to start from a node which we call as U, then we are going to the neighbor, we call the neighbor as V, and if the node V is not visited earlier, we are going to invoke DFS again with respect to V in a recursive manner, so that all the nodes will be read. So, I was showing you a demonstration of how that DFS is going to work for the directed graph. Kindly see this again. So, this is what we discussed earlier. So, you can see very well we put everything into the stack and we are going to the new nodes. So, this is what we were discussing before the break. So, you can see very well whenever there is no further entry, we are popping that. Similarly, if a node is already visited, again we are popping that. So, now you can see very well there are certain portions are totally disconnected from your earlier thing. That is, if we start from A, these nodes are not visited, these are called orphans. We will discuss in the next session called connected components and bi-connected components, where we will try to see the presence of these components in a thing. This uses the data structure called stack. I was telling you that lost in first out is a way, so that the old neighborhood information is not remembered, only the current neighborhood is being utilized for further. You have one more thing called BFS, called breadth first search. So, the difference between BFS and DFS is that instead of going as far as possible, BFS tries to search all paths. So, the difference is, so we are going to use a queue data structure instead of a stack to visit all the vertices of the graph. The difference between queue and stack is obvious. Queue is called first in first out structure, whereas stack is called last in first out. The last entry is the first entry to be serviced in stack. In queue it is not so. You can just compare this queue with the queue of a shop or whatever it is. The fellow who stands in the front of the queue is going to get the first attention. So, we can simulate this particular thing. Assume that we have a graph like this. So, we are starting with a queue. I am going to start with 1. So, I am going to enter the neighbors of 1 onto the queue. The neighbors are 4 and 3. So, 1 I have read actually. So, I am going to the next node 4. So, now the neighbor of 4 I am pushing onto the queue. So, now 5 goes to the queue. So, 4 is read now. So, I am going to the next one, that is 3. 3 neighbors are 5 as well as 2. So, 2 is a neighbor. So, I am pushing that onto the queue. So, 3 I am reading now, I am going to 5. So, the neighbor of 5 are 6, therefore, I am pushing 6 onto the queue. So, now 5 is read, now 2 is read, 2 does not have any neighbors. So, I am going to the next entry of the queue, last entry is 6, I am reading that. So, now you can see very well, this is how this graph is being read. This kind of search is called BFS. DFS as well as BFS are generic searches, and depending on the problem also we can change the searching pattern and we can have different paradigms. Now, we have 2 design paradigms that are included in the syllabus. One is called backtracking and another is called branch and bound technique. Backtracking is a technique where we are going to use DFS in an exclusive manner, and in branch and bound we will use queue data structure in an extensive manner. So, the algorithm for BFS is going to look like this. While queue is not empty, DQ the first vertex u from q, for each vertex v that is directly reachable from u, and if v is unvisited, then NQ that onto the queue and mark v as visited. Initially assume that all the vertices except the starting vertex are marked as unvisited, and the queue should contain only the starting vertex lay. So, in this particular manner we can accomplish BFS for any particular graph. So, now as I said earlier, we are going to use DFS exclusively for our technique called backtracking. So, in this technique what we are going to do is, we are going to deal with optimization problems and we are going to constitute different set of solutions, and we will try to convert this problem into a graph search problem where we are going to search for an optimal solution using a technique called backtracking. To apply this, what we are going to do is, we are going to define the solution as a n tuple. These are the different solutions for the problem. The different solutions are coded in this particular form from x1 to xn. So, now what we are going to do is, we are going to define a criteria. So, we are saying that a tuple which fulfills the criteria effectively is a solution. So, the nature of the problem is optimization problem. What we are going to do is, we are going to formulate all different solutions as a tuple. We are also going to define a set of criterion, and then we are going to check which tuple is able to fulfill the criterion function, and those things we are going to call as the solution vector. So, now you can see very well, if we have n tuples which are the possible candidates for satisfying function p, then you can see very well the brute force approach would be to formulate all n tuples, and then we have to find each and every tuple with respect to the criteria to find out whether it is a optimum solution or not. But unfortunately, this sort of technique is a difficult one, because it becomes a permutation kind of thing. So, if we have 4 items, you can see very well it becomes some sort of a 4 factorial way of arranging those sort of things, and because of these permutations it is very difficult to solve. So, what we are going to do is, to avoid that, we are going to define something called constraints. Constraints are nothing but the conditions that the problem is supposed to fulfill, and if we impose a stringent conditions, then the number of tuples will be reduced. In that particular manner, we are going to solve those sort of things. So, you can see very well in this slide, we are going to define criterion functions pi x1 to xn, and these are called predicates or criterion functions. And if we feel that any of the tuple is not leading to a solution, then all the tuples from I plus 1 to mn may be ignored. So, the success of backtracking lies in the definition of a constraint or restricting functions. There are 2 types of constraints we have. One is called external constraint and another is called the internal constraint. External constraint are rules that forces a variable to take only a particular value. For example, I can put a explicit restriction that x of I should be greater than or equal to 0. If that is the case, I am forcing the variable x to have values only above 0. So, all the tuples that satisfy the explicit constraints define a possible solution space. Some of the constraints are given by the problems themselves. Those things are called internal constraints. Internal constraints describe the way in which xi must relate to each other. So, in this case what happens is that we are taking certain criterion from the problems itself, and using that we are going to restrict the solution space that are existing. I can give you a small example of the nature of problem that are encountered in backtracking. One problem is called 8 queens problem. You must have played chess. So, we have a board, chess board. Assume that we have 8 queens. You know, queens can't be placed in the same row or same column or in the diagonal way. So, 8 queens problem is how you will place 8 queens such that no 2 queens are in the attacking position. So, the strategy is like this. I am going to number the rows and columns from 1 to 8, and I am also going to number the queens through 1 to 8. So, now I can assume that I am going to place every queen in the row I or column I, so that no two queens will be in the attacking position. So, 8 queens are there. So, I am going to define a tuple, a 8 tuple. So, x1, x2 up to x8, where xi is going to be the column on which the queen I has to be placed. So, I am assuming that I have a chessboard, I have 8 columns. I am going to place queen in each column in a sequential manner such that no two queens will be in the attacking position. So, my tuple becomes a 8 tuple like this. So, now I am defining an explicit constraint. Since only 8 queens are there, so I am forcing this xi to take value from 1 to 8, and if this is the case, you can see very well, for every queen 8 into 8 possibilities are there. That means, a queen can be placed into any part of the chessboard. So, 8 power 8 different 8 tuples are possible. This is a very large number. So, if we start searching for answer in this particular tuple, then it may be a very costly affair. So, we are forced to introduce certain implicit constraints. So, the constraints are dictated by the games of the chess. So, since this 8 queens problem involves placement of 8 queens in a chessboard, we assume that according to the rules of the game, no two queens can be placed in the same column or row. So, that means, since we are going to place our queens in the column, we can assume that no two xi can be the same. For example, I can't have a tuple like 1 comma 2 comma 2, I can't, because 2 and 2 are same. Similarly, I can also put a restriction that no two queens can be placed on the same diagonal. Suppose if I put a restriction like that, then many of the tuples like 1 comma 1 kind of thing can be removed. So, because of this, my 8 power 8 is now reduced to 8 factorial. So, now I have 8 queens, therefore, I have 8 into 8 factorial tuples only. So, now I have to search through these tuples for the possible answers. So, the solution for 8 queens problem is these two actually. These are the positions where the queen can be placed, and these are the solutions. So, now you can see very well, the problem is now becoming some sort of a searching problem, where I have all the tuples. So, I am assuming that my answer lies somewhere there, and now the problem of solving becomes searching for the answer tuple that is present in the list of tuples. Instead of solving that as a linear array kind of thing, we are going to introduce the notions of graph, so that these becomes the root of the graph, and the problem becomes something like searching for information or a graph traversal problem. These are the ways in which you can place the queen so that your requirements are fulfilled. This is one configuration. In other words, this is the goal for which we are going to construct the algorithm for that. So, all the tuples are arranged in the form of a tree structure. We can call that as the solution space, and every node in the tree defines a problem state. All the path from the root to other nodes define the state space of the problem, and I told you that the solutions are also available in the state space. Those things are called the solution states. So, solution states are those states leading to a tuple in the solution space. In the whole thing, your answer is there. Those things are called answer nodes. Answer nodes are those solution states leading to an answer tuple, that is the tuple that is able to fulfill your implicit constraint. So, now you can see very well, now the problem becomes searching for a node in the graph, but if we have 8 into 8 factorial nodes, you can see very well the solution space is going to be very bigger. It is very difficult to search for the node, because already we have seen even for a very small graph involving strategies like DFS and BFS takes a little bit of time. So, that means if my nodes are in terms of thousands or millions, searching for that is a difficult task. So, to avoid that, I am introducing these jargons. A node is called a live node, where the node is being currently generated, and I am assuming that for these nodes the children are not yet generated. E node is a node that is being expanded. You can assume that a node that is currently generating the children is called a E node. Dead node is our visited site, a node which already we have read or visited. So, this is a node in our case is going to be a node that need not have to be expanded further. So, what I am going to do now is I am going to use a DFS strategy. So, what I will do is I will generate a children of the current E node, and the children will become E node, and R will become E node again when C has been fully explored. This kind of logic I am going to employ for this paradigm called backtracking. I can also put a bounding functions. In bounding functions, I am going to kill the live nodes, and I am also going to discard the path which may not lead to possible solutions. If I use pruning, this process is called pruning. Pruning is something like a chopping off the nodes that cannot possibly lead to a solution. So, if I use these sort of bounding functions, then this becomes another paradigm called branch and bound technique, where the E node will always remain as E node until it is dead. So, branch and bound exclusively uses your BFS, and if necessary we can also change your search trees to reflect the problems of our undertaking. Suppose if we feel that the solution is present on one particular corner, say for example on the right hand side, then in that case perhaps I can start from that particular side, so that the answer can be found out in an effective manner. These sort of application domain search is called a D-search. So, this is how the tree will be generated. So, I am assuming that n equal to 4, my tree generation will be like this. First node, so when x1 equal to 1, then this children is generated. When x1 equal to 0, this is being generated. You can see this is called a binary decision tree. This involves a second step. And this is also is known as static tree, where irrespective of the problem, this will be generated. You can see for every possibility you are generating a tree like this. This is for x3 level. You can imagine even for n equal to 4, if things are like this, you can imagine how it will be complicated if you have n tuples. So, now you can see very well, you can search the code of everything by tracing this thing. So, 1 1 0 1 is this code. Okay. This node, it is 1 1 1, it is 0. This is x4 equal to 1, this is x4 equal to 0. So, 0 like that. So, you can imagine for n equal to 4, you can see your solution space is so big. If this is a case, imagine what will happen if your number of nodes is 8 factorial into 8. The tree will become very larger, and it is very difficult to maintain this tree structures. Okay. So, this is called the subset. So, now you can see very well, this is the solution space, and somewhere your solution is available, then possibly you can find the answer for this. I can give a layman story for this. Assume that you have a digital lock. You assume that every bit position can be 0 or 1. You assume that your password is something which you have forgotten. If this is the case, how you will start? You will start from 0 0 0 to 1 1 1, and then you will try out all the possibilities. One possibility will possibly open the digital lock. The same thing is what you are doing here. This is a static tree. So, you are generating. So, you are getting all the combinations here. So, now your problem becomes how you are going to search for this. So, this is the permutation tree for n equal to 3. So, now you can see very well, there is a subtle difference. In the previous case, it was like a binary decision, but whereas here you can see, since it is 3, 1 is already visited, therefore, it is 2 and 3. So, now you can see very well, 1 is visited, 3 is visited. So, in the next stage, I will just visit only those that are not visited earlier. So, 1 is visited, 2 is visited, therefore, it is 3. 1 is visited, 3 is visited, therefore, it is 2. So, you can also have a tree structure like this, and this is called a dynamic tree. The earlier one was called a static tree, because irrespective of the problem you had the same structure, but whereas here you can see very well, depending on the problem it changes. Now it is no longer a binary decision tree of the earlier category, where for every node there was 2 paths, but whereas here it is not so. This sort of thing is called a variable tree or the dynamic tree. So, your backtracking approach should be something like this. Whenever a problem is given, you should know how to generate a graph like this. That is the first step. That is called the total solution space, and you assume that in the solution space somewhere your answer is available, that is called the answer node. Then the problem is being restated as a problem, that is finding from your starting point to that particular answer node. So, you are going to visit using DFS. So, you can see very well, you are going to start like this. Already we have seen how to apply DFS. DFS is going to the dead end, and once you encounter a dead end, if there is no way in which you can go further, you can backtrack, you can visit the other node, backtrack, then visit node. You can see very well, whenever a dead end is reached, you are backtracking and then you are going further. So, you can see in this particular manner we can go. So, now let us take some specific examples and then we will try to implement these sort of things. So, 8 by 8 queen problem already we have seen. So, now what we will try to do is, we will try to reduce the problem to 4 queens problem. So, now the problem is how you will place the 4 queens on a 4 by 4 board, so that you will be able to place everything. Okay. So, for the first queen you will have 16 spots, then for the second queen you will have 15 spots. So, these are the different possible combinations that are available, and of course, we will put internal constraint and external constraint, and then we will try to reduce all these combinations. So, now we formulate an algorithm like place your first queen into the first column, second into the second. So, naturally by doing this we are reducing the amount of work. Now, only 4 spots are available for the first queen, 4 spots for the second queen, like that. So, if you do like that, then suddenly you have only 256 different combination that you need to bother. We can still refine the problem by ensuring that constraints are placed. So, now you put a constraint that no two queens will be in the same row or diagonal. So, if you do like that, then your combinations are reduced further. I can give you a small example of how these things are done. So, now this is what your 4 by 4 board, 4 queens you have. The first queen you are putting here. So, by the rules of the game, no queen can be placed here, here as well as here. So, that means I can't place a queen here. So, the next queen I can't place it here, not possible, but the next queen I can place it here. So, I am placing it here. Again consider the possibility, third queen I can't place it here because these two are in attacking position. I can't place it here, these two will be in attacking position. I can't place it here, I can't place it here also. So, that means the placement of this queen is wrong. So, I am going to coming back. This coming back is only we call as backtracking. So, I backtrack and I change this position of this queen to some other position. So, now since we are struck, we go back, then we change this to some other position, and then again I have to consider all other possibilities. So, this sort of thing is what we call as a backtracking. So, now you can see very well the problem looks like a maze where you are making lot of decisions, and whenever you are making a decision and you are reaching the dead end, then you are trying to backtrack. For that you require the last decision to be stored. So, you use that, you backtrack, take a different route, and then you proceed further. By repeating this, you get your final solutions. So, now you can see very well. You can observe how these things go. Now, you see one combination is available. Now, you can see very well these positions fulfill your 4 queens problem. This solution is good because you can see that none of the constraints are being violated. So, now we are going to automate this. We are going to view this problem as a state space tree. So, we start with a empty board at the root. So, whenever we are placing a queen, that means that it becomes a new node. Now, you can see very well your state space becomes like this. This is your empty board, and when you place your queen here, so it becomes a new node. You are free to place this queen anywhere here. So, that means these are the various possibilities. So, by making these alterations, you can see very well you keep on generating the children for each and every node, and if you continue in this particular manner, you will have a very big tree where all possible configurations are being available. So, somewhere your answer is available. So, now the problem is becoming a searching problem. Now, the problem is how you are going to trace from your root to that particular position. So, that is what becoming the solution for this particular thing. Since this tree is so large, we are introducing the notions of a live node, E node, etc., dead node, etc. So, now you can see very well a possible tree combination of 4 queens problem. So, the general algorithm looks like this. This is the tracing of the 4 queens problem in backtracking, and the idea is very simple.